We're obviously in the middle of titrationville here. Last time we talked about titration really of a weak acid with a strong base. And we talked about, sort of the different points along the way there in that particular titration. So we're going to kind of finish up here, talk about one last sort of titration curve here. And this is a little bit different. This is going to be a strong acid, weak base titration. So the setup here is a little bit different. Actually, up in the burette in this case is actually the strong acid. So we have the strong acid up there, and we're actually adding acid to, in this particular case, our weak base, which is down here. So the strong acid being added to our weak base in this case, we do see a curve that is similar to the other one, except sort of upside down. And that is because we are starting with a base. So we are actually starting at a higher pH. And as we add the acid in this case, we're obviously going to be lowering the pH. But we still kind of see that sort of S's curve as we come down here. As we drop down to the equivalence point, again, we do see a significant sort of drop in the pH in this case, because we're adding acid followed by another drop past the equivalence point there, and it levels out. So much like the previous titration curves that we looked at, this one as well pretty much has the same sort of 4 spots that are really important. Obviously, just like before, the first spot is before you really start the titration. The second spot, much like the other ones, is pretty much once you start the titration until you basically reach the equivalence point, or I guess right before the equivalence point. The third spot here in this titration as well, the equivalence point, still where our moles of our acid will equal the moles of the base. And then in this case, you're actually just dumping acid in. And the fourth part would be as you sort of pass the equivalence point. So if we look at it kind of like what we did previously, let's take a look and kind of see what we should end up with at each of these sort of spots. Let's again start with the very first spot, which is obviously like before, at the start of the titration, no HCl or acid added at this point. So in this particular titration example, we obviously have our HCl that we're going to be adding. And in this case, we have our NH3, which is the weak base. So before we add any HCl, really the only thing we got going on is the weak base here. And if I wanted to find the pH of a weak base, what should I do? We should do really a KB problem, right? So we want to do an ice table. We could use the molarity here again of the ammonia as we didn't add anything. So we would do an ice table. And remember, when you're dealing with weak bases, probably a good idea to put the water in that equation. That way you could perhaps visualize the H plus going over, and that will make our NH4 plus and a little bit of hydroxide, right? Which is why this is a base. So since we did not add anything, we obviously can use the initial molarity just the way it comes. Everything else here will be very similar to previous. These will be zeros. Our change will be minus X. We'll have our plus X's and our plus X's happening. And again, here we would have our initial minus X. Again, minus X. We will have our X and our X here. This going into, as mentioned, the KB value, which in this particular example would be this. And at this point, what we would do is, like normal, we would put our equilibrium in there. We would solve for X. However, we need to solve for X. We could again make our assumption and all that good stuff. It is important to remember, though, when we do solve for X in this case, it equals what in terms of pH? It equals the hydroxide concentration, right? So at this point, it is the hydroxide concentration. which does mean you need to kind of go for the POH first and then to the pH at this point. Again, clearly it should be a basic pH at this point since you are starting obviously with a base. Any questions on that part of the titration? So the beginning here is very similar to what we saw with the weak acid strong base titration, except that in that case we were starting with a weak acid, which meant we had to do a Ka problem. Here we're starting with a weak base, so we have to do a Kb problem in this case. Any questions on that there? Okay, so following through our titration curve, just like before, we're going to actually start adding acid in this case. So when we start adding acid, if I could write here maybe. There we go. Adding acid, but we are definitely before the equivalence point. So this means that we are obviously going to get the reaction that's going to occur in this particular example, and that would be our NH3, which is our weak base, plus our hydrochloric acid, which is our strong acid. The NH3 is going to accept the H, and we will get NH4 plus and some Cl minus. Now, you could keep those guys together if you wanted to, but if it's easier for you to follow along with, you could separate them out into the ions. Either way, you know, it's okay. Now, we're just going to kind of do what we did before. So just making up our number. Remember, in this case, we're actually starting here with the weak base, and we are adding our HCl. So if we started, say, with our 4 moles like we did previously here, because we again are before the equivalence point, we definitely should have less moles of our HCl in this case, which is what we're adding. So we'll do our 2 moles and we'll do 0 here. Much like we talked about in the previous one, at this point, the HCl is really the limiting reagent. So it's going to be used up by all of that ammonia that is there. So the change here again will be the HCl. And if you just want to take the whole thought process out of it, it's got to be the smaller number, yes? So you don't get a negative number. It's a good thing to always remember. And at the end here, we end up with 2 moles of this guy, 0 of this guy, and 2 moles of this guy. Why have I just ignored the chloride, by the way? Yeah, it's neutral. So again, sometimes better not to put numbers next to something so you don't try to use it along the way where you shouldn't. So we already know chloride is a neutral salt. Not going to do anything obviously to the pH, so no need really to throw the numbers down there where you might want to try to use it creatively wrongly later on. At this point, just like a normal situation here, we would take obviously our total volume, convert it to liters, and again that would be obviously how much ammonia we started with and how much HCl we added to get to this point, and we would convert these guys back to molarity. Any questions on sort of how the ice table here looks? What we are left with, if we're not sure, we can take a look at our ice table. I got NH3 and I got NH4 plus. Are those things related to each other? They are, right? We have a weak base and its conjugate acid friend. That is also, again, known as a buffer, right? So much like the weak acid strong base titration before the equivalence point, you end up with a buffer. It's actually a acidic buffer. At the equivalence point or before the equivalence point in this type of titration, you actually end up with a basic buffer every time. And that means we can go into our Henderson-Hasselbalch equation. Now, we do want to be careful of a couple of things because this is probably a weak base titration, obviously. We most likely are given the Kb value here. So you can convert it to the Ka and then get yourself to the pKa. You also can just take that to the pKb and subtract 14 to get to the pKa, whichever way you want to do it. But make sure that you are at this point using the pKa value here if you're obviously using the Henderson-Hasselbalch equation. Also, you want to make sure, again, the base, which in this case should be the NH3, should go up on top, and the NH4 plus here would go on the bottom. You also, if you wanted to, could have done a ice table, and you actually have 2 options as to how you could do the ice table. If you converted it to the Ka value, you could do NH4 plus as like the acid and break it apart like an acid. Or you could do NH3 and use the Kb value and get the OH minus and then to the pH. So there's a variety of ways if you wanted to kind of do the ice table approach. You know, if you do it correctly, you could get there. Again, as I mentioned many times, probably less room for error if you just kind of go into that Henderson-Hasselbalch equation. The other option as well is obviously you can use that POH version of the equation with the pKb value. And just remembering that that is the POH and everything's switched around a little bit and you could get yourself to the pH. So there's a variety of places you could kind of ways you could get to the pH at this point in this titration. But the deal is at the start of the titration to before the equivalence point in this type of titration, you will always end up in this situation. You'll always end up in a buffer problem, much like we talked about with our weak acid, strong base. The key here is you need to do at least one ice table. Obviously, the table here is to figure out really the concentration of your buffer, and then you could obviously solve for it at that point. Any questions on that there? So that is, again, the second part there. That brings us to our favorite part, which is the equivalence point here. And at the equivalence point, we are definitely adding stuff. So we'll have our same reaction, which will be NH3 plus a little HCl. Gonna make, and again, I'll keep them separated, but again, it's your call if you want to keep them together. There's really nothing wrong with that as long as you understand what it is. We will initially, again, assume 4 moles. Obviously, we do need to do it in moles because we're continuously adding. And since we are at the equivalence point, since we are adding the HCl, we should know it should be exactly the same amount of moles, and it should be 4 moles. Remember, as we talked about last time, by knowing it should be the same number of moles, and you most likely have the molarity of the HCl, you can technically figure out how much HCl you need to get to the equivalence point. Again, sometimes that is not given to you in a problem. Otherwise, you can do M1V1 equals M2V2 like we talked about last time to figure out the volume that you would need to reach the equivalence point. As long as it's a one-to-one relationship, again, you can use that. So again, I'm going to zero out here my NH4 plus. The change here, we can't choose wrong since it's all the same number. So we'll do that. Again, I'm ignoring the chloride because it's not going to do anything. 0, 0, we got 4 moles. And clearly, like before, we're going to convert this back into molarity. Question on this table here. Yes. Mm-hmm. Yeah. The molarity will not be the same per se, but so there are a couple of situations. If you had the molarity of the HCl, for example, here, and you had the molarity of the NH3, and they actually were the same concentration, you know, say they were both 0.1 molar, right? You would need the exact same volume that you started with to reach the equivalence point of whatever you're adding. So, you know, if we started with 25 milliliters of 0.1 molar NH3, and we're adding 0.1 molar HCl, you would need 25 milliliters of this guy to reach the equivalence point for a grand total of 50 milliliters total to get there, right? Total of everything added, but you would need 25 milliliters. And you could use M1V1 equals M2V2 because it is basically a one-to-one relationship. M1V1 could be this guy, M2 could be this guy. You can solve for V2, and that's how you could get it. You could do a stoichiometry problem, which is essentially what you're doing here, but it's all a one-to-one relationship. If they are not this, you don't have to do any of those calculations. If you do know it's a one-to-one relationship and they have the same molarity, you need the same volume. But obviously, if they are different molarities, you'd probably need to do a little calculation to figure out the volume to get there. It won't be the same volume. Other questions? Our alternative, like I was saying earlier, was if you weren't sure of any of that, but you know for sure that you needed 4 moles of this guy, you most likely will have the molarity of this guy. So again, molarity, which is moles per liter, you have the moles, you have the molarity, you could just rearrange that equation and you could get the liters of how much HCl you would need to add to get there. Probably not in a titration. So in a titration, I would think you would be given the molarity. The only time you might not be if you were asked to solve for something like the molarity of, maybe the acid or something like that. And then that would just be more of a stoichiometry problem, starting with whatever like the acid you added or maybe the base you added and stuff like that. Other questions? All right, so if we do look at our ice table that I now scribbled all over, and the only thing that we got left there is NH4 plus. What is NH4 plus? Is that going to do anything? It is going to do anything. It is going to do something, I guess is a better way of saying that. We know it obviously comes from this weak base, right? Which means it is relatively strong. And what that really means in this case is it is going to go through hydrolysis. So very similar to what we saw with our weak acid strong base titration, we will then need to lay up another reaction where the ammonia part, again, the chloride going to be neutral, not going to do anything, is going to go through hydrolysis. And as we've talked about many times, it's good to understand where it came from. So I know this is a weak base, which means really this is a conjugate acid, which means for sure I know that this is going to act as an acid when it reacts with water. And the definition of an acid is it will give away an H plus, which I know he's going to send an H plus over to this side. So these are the things that you could think about to help you figure out the equation. The other thing that I also know is in this type of hydrolysis reaction, it always makes where it came from. So even if you weren't sure, I know it came from there. So that's for sure going to be on this side. Yeah. And obviously when the H2O gets the H plus, we will make H3O plus. And much like before, without even finishing this calculation, this solution should be acidic, basic, or neutral. Should be acidic because we have produced H3O plus. Also means when we lay up the calculation, what type of K? Yeah, we need a Ka value here. Again, you would probably be given the Kb value in this problem. So that's where we would use obviously the Kw like we've done before to convert it back into a Ka. Initially here, we will do it in molarity. So also why it's really important to convert this back to molarity, just out of habit, just to do it. We would take the molarity obviously from above. And the rest of these guys are going to be zeros. We're going to do some minus x's, plus x's. And obviously here at equilibrium, molarity minus x, x, and x. As you said, we are going to go into our Ka expression using the Ka value. We're going to solve for x, however we want to do that. And now in this particular case, though, when we look at the ice table, x actually does equal the H3O plus concentration, which means that really is the H plus concentration. That means at that point, you can go into your pH equation to get the pH. So much like the previous titration, when you reach the equivalence point here, it does require two ice tables. First ice table is to figure out the concentration of your salt. And you should know automatically it's going to go through hydrolysis in this type of titration. Second ice table is basically a hydrolysis problem where you want to always kind of produce H3O plus and make sure you get yourself to the Ka value. Any questions on this part of the titration here? And again, if we look at the sort of titration curve, we do see that. We do see that at the equivalence point here, whatever that is there. I hope that's basic 5 point something. Again, I think it's 5 point something, and which obviously is acidic. Any questions on that part there? So now we go past the equivalence point and we decide we're just going to keep adding acid at this point. And that takes us to really the fourth part here, which is obviously after the equivalence point. We're going to obviously still have our same reaction. We're obviously going to also do it in moles. And again, we are starting with our NH3. We are adding our HCl. So if we started with 4 moles of our NH3, because we are past the equivalence point, we should hopefully know by this point that we should have more moles, obviously, of the HCl that we are adding. So we'll just make up the number of 6. Keep the numbers nice and not too bad. So just like we saw in the previous titration and the previous one before that, once you really pass the equivalence point, you do get a switch in what is sort of the limiting reagent and the excess reagent. At this point, now our weak base is going to be really limiting, and that means it is what the change is going to be. I'll try to spit that out really badly there. And we will use -4 again. I've said it many times last time. Don't do the negative. You're going to want to. You're going to probably do it at some point, yes, but just know you should not be doing it. And by subtracting 6 all the way across, yes, so that's a very bad idea. So here we end up with 0. We got a couple moles of this guy. We got a fly. We got 4 moles of this guy. At this point here, we're going to obviously convert back to molarity like normal using our total volume at this point. We want to look and see what we got left. We got NH4 plus and HCl. Are those things related to each other? They are not. So again, this is not a buffer. We basically have 2 acids, right? We got this guy here, which will go through hydrolysis, and we have this one here, which is obviously an acid as well. Between the two, which one is the stronger acid? It is the HCl. Again, you're just dumping it in at this point, so you're just dumping a bunch of H plus into that solution consistently. So much like what we did in the previous titration, we are going to really ignore the contribution of the salt at this point, because it really is the HCl that you're dumping into that solution that's going to be the major contributor to the pH. And that really means that we pretty much now have the H plus concentration, which obviously could go directly into our pH. And that will be it. So much like the previous titration, you need to do one ice table here at this point. Really, the purpose of this ice table is to see how much strong base concentration, or the appropriate concentration of strong base, strong acid that you have left over. So how much strong acid you have left over at this point, which then obviously you could go into the pH equation. So this titration, although it looks like it's sort of on a flipped upside down, it really is almost identical to what you got going on in the previous titration. The difference is we're just starting at a higher pH and coming down, as opposed to starting at a low pH and going up, which is what we saw last time. But really the same 4 points here are really the same 4 points that we saw in the previous one. You got basically a KB problem at the beginning. You got a buffer problem before the equivalence point. You have a hydrolysis problem at the equivalence point. And you have like figure out how much strong acid you got left over past the equivalence point. Any question on any part of that titration curve there? All right, well, now we've come to the point of the program where let us just do a problem, right? There's 4 parts. Take about 30 minutes or so. You want to work together, you can, and then we will tackle it here together. So use this time wisely, work it out, so when you take the quiz on Tuesday, you can do it. Okay, so hopefully you made some type of dent in this, yes. So what we're going to do now is we're going to go over together and make sure everybody's hopefully on the right track wherever you may be at this point. So we are going to run a little bit long here, then we'll take a break, and we'll take a little break before we start lab, and we'll start lab just a little bit later. That way we can get through hopefully all of this here right now. So let us take a look. And obviously, maybe the first thing you might want to identify is what type of titration you're dealing with here. Again, if you're not sure if that was a weak acid, that right there should definitely make you know it is a weak acid, because we have a Ka value. So obviously, this is a weak acid strong base titration, which should in your head conjure up something like this. Also should maybe conjure up, you know, the 4 different points we talked about along the way there, and really what is happening at each of those points. Again, this means we have a Ka problem, right? We got a buffer problem, a hydrolysis problem, and then we got some base left over at the end. So again, you sort of know where you're at, you sort of know what type of calculation you should be doing. It should make it a little bit easier along the way. Again, in this case, when it says titrated with, that means that's the stuff up in the burette, the titrate. And obviously we are adding the base there to our acid. So the initial solution is really before we added any sodium hydroxide in this case. So as we've talked about before, clearly at that point, all we got going on is our weak acid. And again, if we already pictured where we are at this titration, we should already know this is going to be a Ka type problem, right, before we even begin. So let us do that. So part A here is obviously before we start, and that is a molarity of 0.1, I believe, right, of the HNO2. Also have a Ka value given to us of 4.5 to the minus 4. So obviously here we're going to take our weak acid, we're going to dissociate it into H plus and a little nitrite, they call that. We again here, because we have not added anything, we could just use the molarity like it came out of the bottle of 0.1 in this case. It's going to be 0 and 0. We're going to do our change, which is minus x, and plus x. And we're going to end up with 0.1 minus x, and x. Any questions on the ICE table here? This obviously will go into our Ka expression, which in this case is the H plus concentration times the nitrite, all divided by the nitrous acid. Again, obviously, no water involved here. We are going to put our equilibrium line in like normal. So that's going to give us x squared up on top, 0.1 minus x on the bottom. And that will equal our Ka value of 4.5 times 10 to the minus 4. We could try the assumption here and assume that x is equal to 0. Was it good? It actually was not good, like a 6.7%. Also a very good reminder that you should check it because it's not going to always work. So I won't waste my time going that way, but you do end up with something like 6.7%, which based on our 5% rule is a little too much. So what we're going to do is quadratic. So we're going to multiply everything that's on the bottom to the other side there. And if we do that, on my paper here, we got x squared equals 4.5 times 10 to the minus 5 minus 4.5 times 10 to the minus 4x, bringing everybody back to the same side. Gets me the quadratic sort of equation or formula there of x squared plus 4.5 times 10 to the minus 4x minus 4.5 times 10 to the minus 5 is equal to 0. That obviously goes into our quadratic formula. So I'm just going to put the numbers in here. So that's going to give me a minus 4.5 times 10 to the minus 4 plus or minus. If you kind of clean up everything inside the square root, you get something like 1.80 times 10 to the minus 4. That if you then take the square root of, you end up with something like 1.34 times 10 to the minus 2. That all will be divided by 2a, which in this case is basically 2. That is going to give us our two x values, and you should yield an x value that is 6.48 times 10 to the minus 3 by doing the plus version of it. The subtraction version, you don't really need the number if you realize it is obviously going to give you a negative number here. Obviously, we cannot have a negative number as h plus is equal to x. So we know that this would not be the correct value, obviously, to use. Otherwise, we do end up with a negative value here, which is not good. Any questions on that? So we will use the top value, which as we can see from our table is basically what H plus equals. So the concentration of H plus here to open up will be 6.48 times 10 to the minus 3, which means we could then go into our pH equation minus the log of 6.48 times 10 to the minus 3. Going to open up our titration here at 2.19 in terms of our opening pH, which is good because it's acidic, right? So it should obviously be an acidic pH at this point. Again, if you got like a basic Something definitely went bad for you here. Any questions on any of these steps? Again, we knew really from where we were on the titration curve that frankly, we should have done a Ka problem like we just did. And obviously we could just do it like a normal Ka problem. Any questions on that part? Okay, so let's go to part 2 there, or part B. And in part B, we're going to actually be adding here some sodium hydroxide. How much? 80 milliliters. All right, so B is, we added 80 milliliters of our 0.1 molar sodium hydroxide. Yeah. Okay, so adding 80 milliliters of 0.1 molar sodium hydroxide to our already 100 milliliters of 0.1 molar nitrous acid. So clearly here we are going to get a reaction since we're adding. So we will do our equation, which will be our nitrous acid plus our sodium hydroxide will give us a little sodium nitrite and a little H2O happening there. We need to do an ice table. Should this ice table be done in molarity or moles? Should be moles. So to get the moles of the HNO2, we're going to take 0.1 times 0.1, 0.1 turning the milliliters into liters, and the molarity is 0.1. That gives us 0.01 moles. For our sodium hydroxide, we're going to convert the 80 milliliters into liters, so that's 0.08 times 0.1 gives us 0.008 moles. This is 0. Again, this is what we're starting with. This is what we are adding. Am I before, at, or after the equivalence point? And before, I know that because the moles of what I am adding is less than what I started with. That automatically tells me I am in that second region, which means before we continue, we should end up with a buffer, right? So we should end up with a buffer. So let's see how we did here on that. The change here is going to be our sodium hydroxide, which means it is the smaller guy in the limiting reagent. So we'll subtract that guy out. Remember, you need to add it on this side. That is going to give us, excuse me, that will get us 0.002 moles, 0 here, and 0.008 moles. At this point, we really should convert it back to molarity. The total volume at this point is 180 milliliters, right? Or yeah, 80. So we had 100 we started with, we added 80, gives us 180. That means we're going to divide each of these guys by 0.18 liters, which is obviously converting that to liters. Gonna break your calculator, pick up your calculator. 0.002 divided by 0.18. Going to give us a lot of ones there. 0.0111 molar for that guy. And dividing our 0.008 by 0.18 will get us 0.0444 molar. Now, again, let's just say that you didn't have the forethought there to think about where you're at or look at the titration curve. You could always, again, look at the table. And again, if you look at the table, this hopefully should remind you that those two things are the only things you have left, and they are related to each other, as we talked about, as a buffer. So we did, as we expected, end up in a buffer situation at this point, which means personally, I'm just going to go right into the Henderson-Hasselbalch equation here. Again, if you wanted to ice table it, you can. So this is going to be our pH is equal to our pKa plus the log of the base over the acid. Our, whoops, come here. pKa is equal to minus the log of the Ka value, which is 4.5 to the minus 4. That's going to give us a 335 there for our pKa value. So our pH would be 3.35 plus the log. The one that's the base here is which one? Yeah, so it's the sodium nitrite. So that is the 0.0444 up on top, 0.0111 on the bottom. And if you do all that good stuff, we're going to end up with a 3.95 pH at this point, which is good because we started at a 2.19. We're adding base, so we are moving upward on the titration curve. Again, if you ended up less than 2.19, you're definitely going the wrong way on this titration. Any questions on any part of that? Yes, sir. No. It'd be great. It's not a lot of calculation doing if it was that. Yeah. So it does obviously depend on the type of titration that you're doing, which we're going to get there next here, I think. Any other questions on this part here? Okay, then let's do the equivalence point here. So we're looking for the pH at the equivalence point. So again, this is a situation where they really didn't tell you the volume to reach the equivalence point. So you could figure it out the multitude of ways I told you. We obviously could see it's a one-to-one relationship, which means technically speaking, we could use M1 V1 equals M2 V2, where here M1 would be our 0.1 molar for our nitrous acid. We're starting with 100 milliliters. Our molarity of our base is 0.01 molar, and we're looking for V2, which would represent the volume of base to reach the equivalence point. And if you solve for V2, it will equal 100 milliliters as well. So that's one way you can figure out the volume to get to yourself to the equivalence point. You would need to add 100 milliliters of our sodium hydroxide here to do that. Also, as I mentioned before, the molarities here are the same, and it is a one-to-one relationship, which means you need the exact same amount of volume to get to the equivalence point, which is what we see here in the calculation. So let us do that then, part B or C, I guess, which is at the equivalence point. So we know we're definitely starting with our 100 milliliters of nitrous acid. That's 0.1 molar. We got our 0.1 molar sodium hydroxide here. Obviously, we will have our equation. So let's just say you, again, didn't know any of that stuff we just talked about, right? We can start here with the same idea. We can figure out the moles of our nitrous acid, which obviously is still the same 0.01 moles. Now that we know we're at the equivalence point, and again, if you didn't know any of that other information, we should definitely know the moles of sodium hydroxide should be what number? Should be the exact same number. That's basically what the equivalence point means. You got the exact same amount of each of those. So you could have just went, all right, well, I'm at the equivalence point, so I know I should have that many moles of it. And now what you have is the moles and the molarity, and you could rearrange and solve for the volume by, again, just simply taking basically the 0.01 divided by the 0.1 will give you 0.1 liters, which is 100 milliliters. So even if you weren't sure about all the stuff we did before, just knowing that this guy should be the same and knowing the molarity, and again, molarity, which is our moles per liter, you could just solve for the liters part and figure out how much of that base you would need. This would be 0. Again, we can't really go wrong here because there's only one number to choose. So we'll choose that number, seems good. That is going to zero us out here. That's going to zero us out here. And that's going to give us 0.01 moles. So you may be asking, like, why is it important to figure out the volume of the equivalence point? It's important right here because now I need to convert this back to molarity, right? So I need the total volume to do that. And in this case, we just figured out I needed 100 milliliters to start with, and I needed one more 100 milliliters to get there. That gives us a grand total of 200 milliliters. So I need to divide this guy by 0.2 liters, which would give us 0.05 molar. Any question on the ice table, how we figured out the volume? Any of those questions? All right, so again, let's just say perhaps you didn't know what step number 3 really should have been. You again can look at your ice table, and we are left here with a salt. Will this salt go through hydrolysis? It will. The sodium part won't, right? Because it's sodium. But the NO2 minus did come from this weak acid here. So it is the NO2 part like we would expect to happen at this point, a little hydrolysis action here. And again, because it comes from a weak acid, it will be a conjugate base, which means it will act as a base here. Plus, it doesn't have an H to give, so it can't give it, right? So it's got to receive it. So it's going to act like a base and receive the H plus. And as we also talked about before, if you're not sure what's on the other side, that's a big hint. Again, it always is where it comes from. So you will end up with your nitrous acid here. And we will also end up with a little hydroxide action. That means, as we know at this point, should this pH be acidic, basic, or neutral? Yeah, we know it should be basic as we have hit the hydroxide there. We are going to do a hydrolysis problem, which is starting with the concentration from above. We're going to do zeros. This is going to be minus X plus X plus X. That is going to be 0.05 minus X, X, and X. This is going to go into our K, which is our HNO2 times our hydroxide divided by our NO2 minus. What type of K is this? This is a KB also because we see hydroxide here tells us we should be using a KB. So we are going to need to convert it. So I'll just do it right there in the center. So our KB will be 1 times 10 to the minus 14 divided by our 4.5 times 10 to the minus 4, going to give us a 2.2 to the 11, I believe, minus 11. So putting our guys in here, that's going to give us X squared divided by 0.05 minus X equals 2.2 times 10 to the minus 11. Any questions so far? That's a pretty small value, so I'm going to make the assumption here and assume that X is equal to 0. And when I do that and run out of room here, I'm going to get X squared divided by 0.05 is equal to 2.2 times 10 to the minus 11. We're going to multiply to the other side and also take the square root of it. And if we multiply to the other side and take the square root of it, we end up with an X value of 1.05 times 10 to the minus 6, which if we check by dividing by 0.5 and timesing by 100, this one though is a happy check here as it all worked out. When we do that and we go back to our ICE table, again, we can see that X actually equals here the hydroxide concentration. Again, not the H plus concentration, but it equals the hydroxide concentration. So the hydroxide concentration here will equal 1.05 times 10 to the minus 6 molar. That again is going to allow us to calculate first the POH, which would be minus the log of 1.05 times 10 to the minus 6. That's going to give us a POH of 5.98. And again here, if you thought for some reason that was your pH, it should not make sense to you because we've already established that the pH should be basic. So you want to make sure that you actually are calculating the pH here, which would be 14 minus the 5.98, giving us a nice 8.02, which is definitely basic at this point. Any questions on any of that stuff? So again, if you understand where you're at, you would know that that is obviously a hydrolysis problem, and it should be basic always at the equivalence point, which I think was a question just a second ago. And this type of titration, when you do a weak acid and a strong base, equivalence point is always basic, like you saw with the acetic acid the other day. When you do a strong acid and strong base, the pH is 7 because you have a salt that will not go through hydrolysis. And when you do a weak base, strong acid, like we talked about before this problem, the pH will be acidic at the equivalence point because you will have a salt that will go through hydrolysis and produce H3O+. So your choices usually for what we deal with is either pH of 7, acidic or basic, and it does depend on the type of titration that you're doing at the equivalence point. Any questions up to here? Yeah. I got it by doing this move here. I multiplied the 0.05 across here and then also took the square root all in one move. Yeah. Yep. Other questions? All right. So the last part here is our good friend number D, where we're adding 105 milliliters of our base in the situation. So D is 105 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar nitrous acid. So much like everything else here, we will have our reaction. Good news is it has not changed here, the reactions. So we'll end up with the same guys. All right, obviously we're still going to be doing moles. So initially here for our HNO2, 0.01 moles. For our sodium hydroxide, 0.105 times 0.1 gives us, again, 0.105 liters times our 0.1 moles per liter gives us 0.0105 moles and 0 here. Now, again, if you're not sure where you're at this point, you don't remember the curve or whatever it may be, you can use your ice table here. So at this point, I have more moles of what I am adding than what I started with. That should tell me where am I on the titration curve. Actually, I'm sorry, it should be 0.0. Thank you. I think the number's right. I think I just wrote it wrong there. Yeah, so it's 0.105, thank you, which is 105 milliliters. Now, am I before, after, or at the equivalence point at this point? After. So again, even if you weren't sure off the bat where you're at, don't overlook what you got in the ice table. It could definitely help you do that. And what we know at this point, since we are past the equivalence point, that's going to now turn our acid into the limiting reagent, and that is going to be our change here. And here we will end up with 0 there. You will end up with 0.0005 moles and 0.010 moles. Our total volume at this point is the 100 milliliters we started with and the 105 that we added. That is 205 as our total volume, which means we will divide these guys by 0.205 liters. That is going to give us a molarity here of 0.020244 molar. It will give us a molarity on the other side there of 0.01 divided by 0.205. That is going to give us 0.0488 molar. So at this point, if we take a look at our ice table to try to figure out what's going on, I got this guy left, I got that guy left. Are they related to each other? They are not. And again, from the knowledge of understanding the titration curve and understanding that we are past the equivalence point, we know that both of these basically will act as a base, right? As we saw at the equivalence point. But between the two, the one that is the stronger base is the sodium hydroxide, right? And then we know that at this point, we ignore the contribution of the salt because the major contributor here is going to be the sodium hydroxide you keep dropping in nonstop. That means really this number here is now our OH minus concentration, which will allow us to calculate the POH by taking minus the log of it, 0.00244. That's going to give us a POH of 2.61. Again, if you got confused or something along the way here and you got to this point and you thought this was the pH, again, understanding of what the titration curve looks like and where you are at, that definitely should not make sense because you should be at the very top. like the other night when you're like, really 12? I got to go to a pH 12. Right. So you should hopefully be at the top, which is not that. So you want to make sure that you do get to the pH, which would again subtract 14 from it and gives us an 11.39. And of course, if you ask me, I would tell you need to keep going to 12, but that would be good here for the answer. So hopefully you can see here that it's really important to understand where you are on the titration curve, what type of titration you're dealing with. And really, like I said, if you really understand where you're at, you should know exactly the type of problem that you need to do. And it makes it so much easier than just trying to jump into it and figure it out along the way. The good news is if you decide to jump into it and figure it out along the way, if you understand the ICE table, it could definitely help you figure out where you're at and what you should do as well.